This is a lecture 22 and today's topic of Lie algebra is definitions of center of Lie algebra, homomorphism, isomorphism, adjoint homomorphism, and examples show that add is homomorphism and find Z of L when L is equal to SL of 2, F. Let's start with the class. So this is the Lie algebra chapter 4, lecture 22. So let me start with the definition of the center. The center of L is defined by Z of L is equal to the set of X belonging to L, where this Lie bracket of X, Y is equal to 0 for all Y belonging to L. Okay, now I will start with the exercise 1.5. Find Z of L when L is equal to SL of 2, F. Okay, now what I'll have to do is write what is your Z of L. Now X belongs to SL of 2, F. Here, can you all see the definition of Z of L? X belongs to L, but here what in the question? The L is equal to SL of 2, F. So wherever there is L, I will be writing this. And then X, Y, in Lie bracket of X, Y is equal to 0 for all Y belonging to L. But what is my L? SL of 2, F. Okay. I'll turn the page. Next is what? Let X belongs to SL of 2, F and Y belongs to SL of 2, F. Now here I will take my X as, this is a matrix, okay? A, B, C and minus A, and Y is equal to U, V, W minus U. Okay? So now what I'll do is I'll take the Lie bracket of X, Y is equal to 0 implies what? XY minus YX is equal to 0. Now this implies your XY is equal to YX. So what I have done, this YX, if I am taking it this side, it will become positive, right? So that's what I have done here. Next I'll turn the page. Now this is what XY. Now what is my X? Here, this into this is equal to Y into X. I have to take this, I'll take it the other side, okay? Now this is my X, Y is equal to YX, okay? So now what I have to do? Now this into this, okay? Now AU plus BW. Then next is what? AV minus BU. Then what I'll have to do is CU minus AW. Okay? And then CV, here CV, minus and minus, it will be plus, right? Plus AU. Okay? Now similar way you'll have to do for this one also. Now this is equal to what? UA plus VC here. Then UB minus AV. Then WA minus CU. Then WB minus and minus plus AU here, okay? Now this is equal to this. Take it here. Now this implies what? BW is equal to CV because AU and AU will get cancelled. So what will remain? BW is equal to CV will remain. Now here what will remain? AV is twice. So twice AV, twice BU. Okay. Here also twice CU is equal to twice what? Twice AW, right? Here. Then next is what? This is equal to this. Now CV is equal to BW. because AU will get cancelled. Okay, this term will get cancelled. CV is equal to BW will remain. Okay, next I hope you all are understanding this. Okay, then I'll turn the page now. Okay, if characteristic of F is equal to 2, then BW is equal to CV is the only equation. Okay, now characteristic of what it is, F is equal to 2, then this will happen. Okay, now this implies what? Now we have taken this BW is equal to CV, right? From here BW is equal to CV, and this is same. Okay, when characteristic of F is equal to 2, this will be the only equation. Now this implies B is equal to C and C is equal to 0. Why is this so? Okay, let me tell you all why it is so. Now if you put in this W has 1 and V has 0. Okay, wait, I'll show you all. Suppose BW is there. Wait. Okay, now I'll show you all here. Now BW is there, right? Is equal to CV. If I put my W has 1. Okay, if I keep my W 1 and V is equal to 0, what I'm going to get? I will be getting B is equal to 0, right? Now if I put V is equal to 1 and W is equal to 0, what I'm going to get? I will be getting this as 0 and this is equal to C, right? Now C is also equal to 0. This is roughly I have showed you all. Okay, now this implies B is equal to C is equal to 0. Hence W, V are arbitrary. Now this implies what? X is equal to, let us see what was our X before. This was our X I have taken, right? A, B, C minus A. Now here what happened is the value of B and C is 0. So X is equal to A, 0, 0 and minus A. So that's what I have written it over here. Okay, X is equal to A, the value of B is 0, the value of C is 0 and minus A. And A belongs to F. Now this implies what? Z of L is equal to set of, now what is this set of this X where A belongs to F. Now this A belongs to F. Okay, now I'll turn the page. You all can see the image clearly, right? Okay, now I'll turn the page. Now if characteristic of F is not equal to 2, then what is going to happen here? Then BW is equal to CV and this. I'm taking this all now. Okay, BW is equal to CV. This and this is same. So okay, AV is equal to BU and CV is equal to AW. So this is what I have written it over here. CU is equal to AW and AV is equal to BU. Okay. Now this implies the value of A, B, C is equal to 0 has U, V, W are arbitrary. Here also I'll have to do the same thing. If W is 1 and V is 0, I will get B is equal to 0. If U is 1 and W is 0, then C is equal to 0, right? If here my V is equal to 1 and U is equal to 0, then what I'm going to get? A is equal to 0, right? So just an example I have given you all. Okay, now this implies what? Z of L is equal to, now A, B, C, D, this all the values will be 0 in this case. Okay, now I'll turn the page. Next is the definition of homomorphism. Now what is a homomorphism? If L1 and L2 are Lie algebras over a field F, then we say that a map phi from L1 to L2 is a homomorphism if phi is a linear map and phi of leaf bracket of x comma y, and this is the normal bracket, is equal to leaf bracket of phi of x comma phi of y for all x comma y belongs to L1. Now x comma y will belong to this L1. Okay, I hope this definition is very important. Please understand and do this definition. Okay, now I'll move to the definition of isomorphism. Now what is an isomorphism? See, if L1 and L2 are Lie algebras over a field F, then we say that a map phi from L1 to L2 is isomorphism if phi is bijective map and phi of x comma y is equal to, this is a Lie bracket of x comma y is equal to Lie bracket of phi of x comma phi of y for all x comma y belong to L1. So what is the difference between homomorphism and isomorphism over here? Here your isomorphism, this map is homomorphism if phi is linear map. It should be linear. Here the map is linear and here it is bijective map. For that it should be what? 1 1 and on 2, right? So that's the only difference. And this definition, please learn them. Next is adjoint homomorphism. Now what is an adjoint homomorphism? If L is a Lie algebra, we define adjoint homomorphism add of L from L to GL of L by add of x is equal to add x. Okay, this is the bracket, Lie bracket. Okay, now for all, just a bracket. Okay, for all x belong to L and add of x, okay, and add of x L from L by, this is given by what? Add of x into y is equal to Lie bracket of x comma y for all x comma y belongs to L. This is one more definition which you all please do learn. This definition is very important to solve the upcoming theorems, proofs, etc. Okay, I'll turn the page. Now this is the example where I have to show that my add is homomorphism. Okay, now to prove that, take add of x comma y is equal to add of x into add of y minus add of y into add of x. So first I'll take this into z, okay, which is equal to, now this I will be writing it as what? Inner product of x comma y comma z. Now this is equal to minus z comma x comma y. Now how I got this minus thing over here after this? This is due to the this thing. Have you all come across the formula like this? X comma y is equal to minus y comma x, right? So we have used that formula, like it is, I think, alternativity under that one example which I proved in the previous lecture. It is that. Okay, so that's how you get this step. Okay, now this is equal to what? X comma y comma z plus Lie bracket, okay, there's a Lie brackets, plus Lie bracket of y comma Lie bracket of z comma x. Now this is by Jacobi's identity. This step I got by Jacobi's identity. Okay, now this is equal to what? X Lie bracket of x comma adjoint of z add of y into z plus y minus Lie bracket of y minus add of x comma z, meaning not comma, okay, add of x into z and then put the bracket. Now this is equal to add of x into add of y of z minus, now finally this is the final statement when I am removing this from the Lie bracket, minus add of y into add of x of z, right? So finally we have proved that add of x is a homomorphism. So this I want you all to prove this, and then you all can check whether you all are getting the same thing or no. Okay, and just comment below whether you are getting the same or no. So now, okay, next I will be doing then one more proof in the next lecture. So I'll end up my today's lecture here only, and thanks for watching. Thank you very much.